Okay, so let me get started. This is a reminder, so our goal, and so I'm going to continue on Monday, a week from today. That will be the last lecture, and we'll see. I hope I can get through a proof of a theorem, at least sketch a proof of a theorem about dynamics of vortices in Gaussian FC. A lot of time, as you have seen, is spent building up machinery that's used for the proof. Okay, and so our goal now is to look at the relationship between the energy and the vorticity, and this will help us prove theorems later on. Okay, and so the theorem, so we've done most of the work, and so the first theorem is one that says, okay, we assume we have a domain, and there are a bunch of points who are separated some distance away from each other and away from the boundary. And I consider a function psi, and I know that the vorticity looks kind of like delta functions near the points. And so in this norm that measures the extent to which the vorticity resembles delta functions, well, the right-hand side is say small compared to the intervortex distance. And the energy is not too big. The conclusion is that, in fact, the vorticity is very sharply localized around some other points. If I change the points A to some points C, then the vorticity is very sharply localized. Let's see. Okay, I have to get rid of something here on my screen, which is confusing me. Okay, so and so we've done most of the proof. So what we've done is we've shown okay, so I put this here for the definition of degree. The degree is the winding number. And so what we said is that in order to prove the lemma, it suffices to find a bunch of very small balls who contain the set where the function psi is small, and with knowledge about the degree. Okay, and so this tells us what we need to do to prove the lemma, to prove the theorem rather. And then the main tool is this proposition, whose proof we discussed last time. And so the proposition says, essentially, given any sigma, so in our context, this sigma naught is like epsilon log epsilon, some very small number. So given any sigma larger than, say, epsilon log epsilon, we can find a bunch of balls who cover the set where the function psi is small. So here sigma is a parameter. They cover the set, then the radii grow as sigma increases. The radii grow, at least for balls who are contained in the set cal D, in the set D. The radius is proportional to the degree. And then we have this lower energy bound. Remember this lambda epsilon? This is like pi log of sigma over epsilon up to a constant. So we have greater than or equal to if I allow for this constant. Okay, let's see how we can use this proposition to prove the theorem. And I'll just, we can do this almost with a picture. This. Okay, and so, so the setting of the theorem is this. We have a domain. And we have some points. Let's imagine, to keep the picture from getting too complicated, let's imagine there are 3 of them. So there's a A1 and a A2 and A3. And what we know is that the vorticity minus this rho sub A is the minimum intervortex distance, or the distance to the boundary. Okay, and so then we apply the proposition, and we'll choose, so we apply the proposition with sigma being epsilon to the beta. So what does it tell us? It tells us we can find a bunch of balls. Let's look. We can find these balls such that well, okay, so such that for any ball strictly contained in the interior, the radius is like epsilon to the beta times the degree. And so if the degree is non-zero, we have if the degree is non-zero, then the radius is some multiple epsilon to the beta. Let's put absolute values here. That. Okay, and so what's going to happen? So I know that the total energy in the proposition is like m pi log 1 epsilon plus a constant. And so we have the integral over the domain of the total energy. That's like m pi log plus a constant is bigger than this. And this is bigger than the sum over the balls of the integral over the ball of the energy. And okay, I really mean the ball intersect the domain. And that's bigger than the sum of the radii times this. And so well, let me put the sigma here. So sigma is epsilon to the beta. This is like and so this is log epsilon to the beta over epsilon. That's well, let's write it. And that'll be 1 minus beta times log 1 over epsilon minus a constant. Okay, and so what I see is that oh, where did I go? Okay, so this is a little bit of a mess, but what I can see is that if I can then divide both sides by log 1 over epsilon, let's cancel this, and there's a pi here too. Let's cancel that. And so what I find is that the sum of the radii divided by this parameter sigma is basically is bounded. So you know, plus, you know, there may be some error terms, but this is the leading order behavior. Okay, just by comparing this and that, and sigma, of course, is this is supposed to be a sigma, which is epsilon to the beta. Okay, and so the sum of, and so these are small balls. The sum of the radii is a power of epsilon. Okay, and so I can picture them as being, well, they're here. And so what else? So then you see this previous lemma says, once I can cover the set where the function is small by small balls, then, and so now we have, this is like epsilon to the beta times a constant, basically. Okay, and this is like log epsilon absolute value. And so, and so the vorticity is really well approximated by just putting a delta function at the center of each ball with the degree of that ball. Okay, and that tells us, but we already know by hypothesis what the vorticity looks like. The vorticity, well, let's review this. And so this whole thing is less than C epsilon to the beta prime. I take some slightly smaller exponent, beta prime, if I want to. And so a tiny number. Okay, and so here I have these balls, and but on the other hand, I know. So what do I know? So I have these. This is like let's move this over here. Okay, so on the one hand, I know that the vorticity is by hypothesis, is not too far from these delta functions. I have this hypothesis. On the other hand, I know this about the this collection of balls, and so this tells me that well, I better have so it tells me that the two sums of delta functions are close to each other, which means that in this sum, all I can do is I better have a center near each of near each of the a sub j's, and I should have the same degree d sub j. Okay, so there'll be a C2 over here someplace, not too far away, within this distance rho sub a over 10, and then there'll be a so the balls will have a like C1. If I can number them this way if I like, and C3, and there may be other stuff. There may be other balls, but they're small and they have degree 0. And so they don't contribute to this they don't contribute to the sum of delta functions, or there may be things on the boundary and I can ignore those too. Okay, and so by comparing my hypotheses with what this construction of balls tells me, I find that my configuration of balls has to look like this, and this tells me exactly what I wanted to know, which is that, well, by it tells me exactly that, right, so again, the point is that there has to be a contribution for each of the a sub j's, and there can't be anything else going on. Okay, and so the conclusion is that then indeed, okay, by decreasing beta prime to alpha and by taking epsilon small enough, I can assume that this is true. Okay, and so this is the conclusion. Okay, and so the point is, again, control over the energy plus some crude information about vortices tells us that, in fact, the vortices are very sharply localized, and we can find places near the original centers. I didn't even record all that stuff in the statement, where this occurs. Okay, and again, this follows from just sort of crude estimates on the boundary of each ball, and then there's this argument for taking sort of seeds and letting them grow and merge in a certain way while preserving estimates. And so that's how that goes. Okay, that's one of the main ingredients of the proof. And so the other, and so we really just applied the proposition with a certain choice of sigma to guarantee that the collection of balls we produce is small in the sense that the radii added to a small number. And then we've compared that with hypotheses, and that gives us information on what the collection of balls must look like. Okay, so next, so what I want to do now is, at this point, we're entitled to assume that so we imagine analyzing some solution of the gross PTFC equations, and we may be entitled to assume that for that solution, something like this holds, that we have points around which the vorticity is very sharply localized. And I want now to look at the consequences of this information for the energy. And so far I've said if we know something with the energy, that tells us something with the vorticity. And now I want to look at the other implication. If we know, say, this about the vorticity, can we get refined information about the energy? And this will require introducing some notation and some auxiliary functions, which we've seen before, but let me remind you, these are, okay, let's look at them. Okay, and so I'm always assuming that my domain is bounded, simply connected with smooth boundary. And first, so this is in a way a review of things we talked about with the Euler equations. So I want to imagine first that I have, okay, I'll discuss the difference between Euler equations in a second. I'd like to imagine that I have a domain with m vortices, m point vortices located at points C1 up to Cm. And so I imagine these are the points I find by applying the previous theorem. I start with some points A1 up to AM where the vortices are roughly localized, and I move to the nearby points C1 up to Cm where it's very sharply localized. Okay, but let me imagine an ideal situation where the vortice is just a sum of delta functions at these points. And okay, so the big difference, or a big difference between Euler and Gross-Piasecki is that the vorticity in Euler is naturally quantized. And so these d sub j's, these numbers are naturally are integers. That's a natural function in this context. And somehow, if the degree has absolute value 1, then they're sort of stable, and if the degree is more than 1, they're unstable. Let me not say much more about that, but I'll always assume that the degree is 1 in absolute value. So rather than considering arbitrary configurations of vorticity, I'll always assume that we have these degrees or winding number all being plus or minus 1. Okay, and then and this pi is a natural normalization in this setting. So okay, and so for such vorticity, but then okay, so at this point, the Gross-Piasecki character of this discussion manifests itself only in that I've chosen vorticity of the special form with the di's being plus or minus 1, which is a factor of pi. Okay, so then well, here's another way. And so for Gross-Piasecki, it's convenient to put a factor of a half in the, so this factor of half wasn't there for Euler. So I say the vorticity is a half the curl of the, so the velocity field J star, the current, is related to the vorticity in this way. The 1/2 the curl of J star is the vorticity, and the divergence J star is 0. And then I assume that the J star is tangential along the domain boundary. That's this assumption. Okay, and so this is how I define the velocity field associated to a given configuration of vortices. That's here. And then let's just write down rather explicitly what it is. So, and again, as we did with Euler, we can recover the velocity field by looking at a stream function. Given the vorticity, we invert the Laplacian, get a stream function, and then the velocity can be found by taking the orthogonal gradient of that thing. And so here's the stream function. And I've gotten this wrong as usual. So this should be no, this is okay. Okay, so this was correct, in fact. Okay. So if I have well, this should be familiar from Euler equations, I hope, if we remember. Okay, and so the and so this is for single vortex at a point C. The stream function would be defined in this way. And then for a bunch of vortices, I just have a superposition. Right? So the relationship between the velocity and the vorticity and the stream function is all linear. And so, and let me define K here as the orthogonal gradient. Okay, and so k of x comma c is exactly the velocity field generated by a vortex at the point c. So it's a velocity field whose divergence free tangent to the boundary and whose curl is a delta function at that point. Okay, and so right, so we can find this by finding the stream function. And note also we can see that this stream function we can write it as follows. So I write the stream function as a sum of two pieces, this log and another piece h. I've changed y to c for some reason, doesn't matter. Okay, so if I then, and so this equation you can think of as being the definition of h. H is what's called the regular part of the Green's function. If I apply the above equation, if I take the Laplacian and the x variable of both sides of this, I'll find that the Laplacian of g is the same thing as Laplacian minus log. And therefore the Laplacian of h vanishes. H is harmonic. Okay, so the equations for g in the definition yield these equations for h. I can see that if g vanishes when x is in the boundary, then h is equal to minus log for x in the boundary. Okay, so this is the regular part of the Green's function. And remember a long time ago when we talked about point vortex dynamics, we said, for example, if I have just a single vortex in a bounded domain, its velocity field will be this k of its velocity field will have a contribution from this h, the orthogonal gradient of h of x comma x. Okay, and so then the Biospheric kernel, I think I wrote this before, is here. And then, okay, I'm not sure, I think I didn't introduce this. And so so given a configuration of vortices, so I'm always imagining that I have the vorticity. Which is pi times the sum of d sub I delta c sub I. So the velocity field is a linear combination of some of these things with y replaced by c1 up to cm and with right signs. And so I can see that this velocity field diverges around each of the vortex locations. But I can compute the energy, I can at least estimate it by doing the following. I'll draw a picture. So if I have a few of these vortices, again, the velocity field diverges like 1 over r, 1 over distance from the vortex near the vortex. And so it's not in L2, it's not locally in L2. But I can cut out a ball of radius r around each vortex, compute the L2 norm on the domain with those balls removed, and then subtract out. So if I do this computation, I'll see that the integral diverges in a certain way as r goes to 0 because the whole thing is in L2. But if I subtract out the diversion part, I can then pass to limits and get a finite number. And one can do this computation. And the finite number that you get is just this thing. It's a function of the positions and the degrees of the vortices. And this is what it is. So it involves these logarithmic interactions. And it involves this thing h, the regular part, which is sometimes called the Robin function, I believe. Okay, and so if we did this on all of R2, by the way, okay, we'd also have to renormalize it. We'd have to subtract some potential infinite contribution infinity. But if I did this on all of R2, we would just get the logarithmic contributions. If you do it correctly on R2, you see that there's some kind of effective energy, which is just the sum of the log of Cm minus Cn. And we can see here, by the way, if two vortices have the same sign, if d sub m is equal to d sub n, then the corresponding term will diverge as will go to plus infinity as m and n approach each other. So minus log blows up as the distance goes to 0. So the energy of a pair goes to plus infinity if they have the same sign, if they approach each other, and minus infinity if they have opposite signs. And so we can say, two vortices of the same sign repel each other, and like signs repel, opposite signs attract, in terms of energy at least. Okay, let me see. I'm going to omit this calculation, but it's not. The point is, what is this? This is the it's this, and if I'm squaring it, it doesn't matter if the orthogonal part is there or not. And this function psi is harmonic on the complement of the balls. And so you can anyway by parts and easily see what's going on. It reduces to the integrals of the boundary. The outer boundary doesn't contribute to anything because psi vanishes there. And so you look at the boundary of each ball, and that's one can just look at it and see what's happening. Because everything is rather explicit in these harmonic functions. Okay, so then the next thing I would like to say is that then there's a construction of this, so returning to gross Petievsky. So all of this has just been about divergence-free vector fields whose curl is a certain sum of delta functions, basically. But returning to gross Petievsky, I claim that one can construct a gross Petievsky wave function with given vortices, and so this is a function psi. So given some configuration of vortices, these x's and these d's, as here, one can construct a wave function psi such that the vorticity of psi is very close to the given configuration of vortices, and the energy of psi. Well, okay, there's a natural construction. Let me describe the construction. Let's write down a J star. Such that the okay. And so we can do this rather explicitly in terms of logs or rather the orthogonal gradient of logs and this Robin function, this function h we defined, the orthogonal gradient of h. And then I want to find, say, psi. So eventually so psi star going from d minus these points to such that the vorticity of such that this is true. Okay, how do I do this? So this says that the well, in fact, let's say we want J of psi star to be this J star. where we recall that J of psi star is the I psi star grad psi star. Okay, and so and so if I have a function of unit modulus, and I write J of psi star, or sorry, I write psi star as EDI phi, then J of psi star is the gradient of the phase. Okay, and so so I can see the right, and so the point is, well, if I know from calculus, from vector calculus, if I'm given a gradient vector field, how to construct the function whose gradient it is. So I just integrate along. I fix a point, and I integrate along paths. I integrate the gradient vector field, and I say that the value of I can define. So we should have phi of x minus phi of, I don't know, x naught is the integral j of psi star dot tau, where this is a path from x naught to x. So I guess I'm setting, I set phi equals 0 at the point x naught. I don't think it matters. And of course, we also know from vector calculus that in order to do this, I need the curl of the vector field to vanish. And here it doesn't quite vanish. The curl is equal to a bunch of delta functions. But what this says is that if I go around a well, for example, if I go around a path from x naught to x, if I go around it in two different ways, well, if I by looking at the difference of the paths, I can see that the difference of the number I get by going along path 1 or along path 2, it's just the integral along the closed path and closed formed by going first along path 1 in one direction, along path 2 in the opposite direction. Okay, and that may fail to vanish, but it's always an integer multiple of 2 pi because these the curl is delta functions multiplied by 2 pi, and so if I go around this path, I'll get some multiple of 2 pi. And so what this says is that the function phi constructed in this way is well-defined modulo 2 pi, which is all I need because I'm going to put it in the complex expansion. Okay, and so we can do this, and then 3 we modify psi star near each c sub I, modify the modulus to get some psi star epsilon, and we do this in an energetically optimal way. Okay, and so, but I can see that if I do, and so I can just do the say in an epsilon neighborhood at each point. And so then what happens? Then Well, so note that, so outside, and I'll say that psi star epsilon is psi star outside balls of radius epsilon around these things. So if I then look at the domain and I subtract these epsilon balls, union of them, let's call this d epsilon for convenience. If I do this, well then outside these balls, the modulus is 1. And so I'm really looking at so there the psi star epsilon is equal to psi star, a factor of a half. And what is psi star? Psi star is up here. There it is. And so this is really going to be the gradient of the phase. Well, this is really equal to 1/2 j of psi star, which is this j star. Okay, and so I can see that the energy, the energy of the thing I've constructed is very close to the energy I earlier asserted without giving the details that we could compute this energy and get its asymptotes very precisely. Okay, and so in this way, and so then there's some constant gamma. This is the, if you do the construction the optimal way, you would get, right, so here I'm imagining I take R to be 1 over epsilon. I take R to be epsilon. And then I see the energy is like m pi log 1 over epsilon plus some contribution from inside the, plus this W plus some contribution from inside the core, which I do in a smart way. And I get an optimal contribution. Okay, in fact, this may be, I may have lied a little bit in places, but this is the idea. Okay, so, all right, and so then let me ask any questions. So, okay. And so this is m pi log 1 over epsilon plus this W plus and then there'll be some order 1 contribution from inside the balls. That's the idea, and that may be this constant gamma. Okay, I really misstated this a bit. Idea. Okay, and so then let me state another theorem, and I'll so here it is. Okay, so I've described a construction of a candidate for something that, for what a Gross-Petyaevsky wave function might look like with sort of, say, energetically optimal if I know the vortex locations. And so this theorem states that indeed the construction I just described yields a wave function whose energy is very close to optimal given those vortex locations. And in fact, we'll get some extra information from this. And so here's the assumption. And so the assumption is, you see, I'm entitled to assume this because of the previous theorem. So I can easily engineer situations in which I have some function psi in H1 whose vorticity I know to be very close to a bunch of delta functions. And I'm assuming O is at the, so this rho sub psi is the minimum intervortex distance or the distance of any vortex boundary. So every vortex is contained in a ball of radius rho sub psi in which there are no other vortices in which it doesn't touch the boundary. And that's it's bigger than some constant rho naught. Okay, and so then I'm entitled to assume that the vortex is very well approximated by the sum of delta functions. And what does this tell me with the energy? What it tells me is that the energy is well, okay. First, let's ignore all this stuff. We'll look at it later. So it tells me so the point is this is a tiny number. This is basically 0. So the left-hand side is basically non-negative up to very small errors, and that tells me that the energy of this wave function psi, if it only satisfies this concentration condition, is almost bounded below by this explicit construction I've just described. Okay, and so in other words, it tells us that this E epsilon of psi is basically that this psi star epsilon is really close to being energetically optimal for the given configuration of vortices. Okay, and so that's one thing, but it tells us more because there's all the purple stuff I crossed out. Let's uncross that out. So this energy can't really be smaller, up to small errors than this rather explicit number. I can compute what this is, and moreover, this energy has a kind of coercivity. In other words, if the energy of psi, so this says if E epsilon of psi minus E epsilon of psi star is small, then psi well, it tells us ways in which, okay, in quotation marks, psi is like psi star epsilon. And so first of all, this is the energy of the modulus. And so this is the, the gradient squared of the modulus over 2 plus this modulus squared minus 1, that's squared root of epsilon squared. Okay, and so this tells us that the gradient modulus is small and that the modulus is not only close, not only epsilon like log epsilon, close to 1, but it improves that estimate. Okay, so we get an improvement here, and this also tells us that. So again, we should think of this as being psi is like rho EI phi. This says that rho grad phi minus okay. Here I should point out I'm staying away from the vortex locations, and so if I cut out small balls around these points, like CI, so I cut out these balls, then in that region, I have a lot of control over both the modulus and the phase of this function psi. Okay, this is what this theorem says. And so the plan for the remaining 3 lectures is I want to give, well, let's see if we can, so this actually isn't super hard, but it's certainly takes more time than we have left, than we have time to do. We can't do both justice to this and the dynamics results. And so let's give the idea anyway, if we can. Let's start. Let me see. So let's let, so for J stars above. Okay, so J star is the ideal velocity field, divergence-free tangent along the boundary generated by vortices of the given circulation at the given points. So let me see. Let's do this. So let's say E epsilon of psi minus 1/2 J star squared. What is this? So I'd like to simplify this. Okay, and then I've done nothing so far. So let's say grad psi. I think I've done this before, maybe. So this is just writing. So I'm thinking of okay, for each component, dx1 and dx2 of psi. Each of those is a vector in R2. I can write it as a sum of components in the direction of as an orthonormal basis for R2, and the orthonormal basis is given by psi over its modulus and I psi over its modulus. Okay, so this is just linear algebra. Oops. Okay, and so then if I square this, and remember this, what is this? The first term is just, I believe, right, it's that. And the second term is J of psi times over psi times I psi over this. Okay. And so if I square this, you see these two vectors form an orthonormal basis for R2. And so I'll just get the gradient squared of the modulus plus J plus this. Okay, and so then if I combine, say, this and this, I will get. Well, okay, I'll get just the energy of the modulus. Okay, that takes care of this, and then I'm left with plus 1/2 J of psi over psi squared minus J star squared. And let me rewrite this. Let me see, what do I want? I'd like to have this. Okay, if I do this, then I'll have a, well, I'm going to write this down and I'll see if I got it right. Okay, so let's see if this is right. I may have to fix the sign. And so here I have a j star squared over 2 from here. I have a j of psi squared over 2 in both cases. I have a cross term, j of psi dot j star, with a plus sign here and a minus sign there. So those are good. And then the other terms are, here I have a minus 1/2 j star squared over 2. Here I have a plus 1/2 minus 1. And so this is correct. Okay, and so so what I need to do to prove and so the idea is well, maybe I'll so what I need to do is to show that you see I'm comparing the energy of psi star is really just the integral of this thing. And so so on the well, okay, maybe I'll stop here. But from this we can we can stare at this for a few minutes and see sort of the idea of the theorem, which we'll do on Wednesday. And then after not much more discussion, this will start using this to prove things about the dynamics of point vortices in gross Pittiansky. Okay, that's it for today. Any questions? Let me see if there's anything worth uploading. Oh, okay, we'll upload this. And I'll drop this in the chat in a second if I'm able to do this this time. Last time somehow I was unable to. I don't know what the problem is. I'm having. Wait. So where is this? Come on. Okay, let's do this. And I'm trying to. Okay, so it's working this time. Okay, so I've added that file to the chat. And in the meantime, are there any questions? So all I'm really doing is calculus, but I'm not sure how digestible it is because I'm in the interest of time, I'm forced to skip some details. And so I hope it's not too tough. Okay, questions?
Hi, Professor. I have a question about the Navier-Stokes equations.
Okay.
Yeah, if we have 2-point vortices about the Navier-Stokes equations, can we hope the similar results holds as Euler or gross Pittiansky?
Okay. Yeah, so for Navier-Stokes equations, what happens is, well, okay, so the simplest, so good question, thank you. So the simplest situation for Navier-Stokes is if you have a single point vortex. And so we don't expect to do anything dynamically interesting, but there you can really solve the equations with the initial data being a delta function at the origin, say.
Yes, I know it's called Olsen vortex. Yeah.
Yeah,
but for 2-point vortices, can we imagine? Or for example, if it has different circulations, can we imagine that it may rotation
so
around?
For people who don't know the Olsen vortex, and so what it is it's a Gaussian, and it spreads out as time grows. And so and I think the radius is like the square root of time. And so for if you have 2-point vortices, what people expect is that you see, what I always want is for the size of the vortices to be small compared to the distance between the vortices. And so for Navier-Stokes, this will be true for a while because, but the vortex is growing. And so the kind of theorems that one have would, well, so if you consider the vanishing viscosity limit for Navier-Stokes, then you could recover the sort of things you've seen earlier. Or if you consider, say, widely separated vortices for fixed viscosity, then for a time whose maybe the square root of the viscosity, something like that, one should see the same dynamics. And so for Navier-Stokes, things like this are true, but only as long as the scale of the vorticity is small compared to the distance between the vortices.
Thank you.
You're welcome. And there are results of this sort due to people like Thierry Gallet and their right. Okay. Other questions?
I got a quick one as well. Hi. And I was wondering, so I guess in general it's very hard to reconstruct the wave function psi from if you only know the density and J, say, you know. I guess this is in general not possible. So the only time you need to use this is for this, say, for this psi star, where you actually can do this. But all the other times it's for you is kind of enough to be close to this psi star, so you don't need to reconstruct effectively the wave function from.
Yeah. So what this theorem says is, right, so psi star is characterized by some kind of energetic minimality property, and so what the theorem says is that if I know where the vortices are, and if the energy is close to being optimal given that configuration, then that gives me a lot of information about what it looks like. So not enough to allow for pointwise reconstruction, but we can reconstruct it with errors in L2 that we can kind of control, at least away from the vortices. Yeah, you're right. In general, it's very hard to construct a wave function. But in this regime of near energetic optimality given vorticity information, then we can actually extract quite a lot of information. I don't know if that answers your question.
Yeah, it does. And say in this, and then when you wrote the psi of a modulus of psi, so the phase. So is this always well defined to write this? Say your.
Let's see. No, not always. No. But let's see. What did I write? I should have written psi star there. I probably wrote it all wrong. Let me check. Yeah, so that was, okay, let me go back and share the screen again. It's not that wrong, what I wrote. Oops. Okay, so, right. Yeah, so here, that's right. So this is not so well defined if psi vanishes. But I guess the point is, well, either that happens on a set of measure 0, or if it happens on a positive measure, then the gradient vanishes on that set anyway. And so, so this decomposition makes sense almost everywhere.
Okay, that's true. Yeah.
Yeah, that's
okay.
But a good point. This is a bit dangerous. What I'm really doing is just writing, I'm really just doing this decomposition, but it's using this language of the little j allows me to avoid asking, is there really is the phase well defined, and so on and so on. So that's what I'm doing.
So this little j is really, say, it's almost like considering the velocity field, no? Say.
Yeah. So well, j is the.
Say, so it's one could think of it like the density.
Exactly.
Like rho times v, you know?
Exactly. Yeah. Yeah. And so yeah, this is the velocity field, and this is the density, and so it's the. So this is why it's really I think, literally true to call it the momentum density. The momentum is mass times velocity, and so this is the local mass, the density times the velocity. Yeah, so it's and because rho is 1 most of the time, this momentum density is very close to being the velocity. Yes. Okay.
Thank you.
Welcome. So good. So then, if there are no further questions, then I'll sign off, and I hope to see you on Wednesday.